Welcome to Breaking Through to Another Side, bypassing firmware security boundaries from embedded controllers in Lagoon GHI with Alexandre Gazet and Alex Matrosov. Before we begin, a few brief notes. Stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on Level 2. The Black Hat Arsenal is in the business hall on Level 2. Join us for mimosas at 11:50 and ice cream social at 15:20, both in the business hall. Lunch is in Bayside AB from 1 to 2:30. Don't forget the merchandise store on Level 2 and session recordings from SOK. They have a desk on every level. Thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick up. Please use the microphones in the aisle for any questions following the talk. And with that, let us welcome our speakers.
Good morning, everyone, and thanks for coming this early morning slot, especially after all these crazy parties Black Hat yesterday. And bypassing firmware security boundaries from embedded controller, it's our topic for today. And I'm Alex Matrosov, embedded security lead from NVIDIA, and Alexandre Gazet from Airbus Cyber, security researcher and great reverse engineer. So first of all, we want to make a small disclaimer because everything which we discover in this presentation, we did over reverse engineering techniques and methodologies. So we can be wrong in some points which we made it in this presentation, but maybe not. So, and we literally spent 5 months of reverse engineering BIOS guard technology, and it's a lot of information about BIOS guard which has never been in public before. So we have some introductory part about the hardware security boundaries problems, what that means, where the limitations are, and how the attack surface looks like. Then we will make a deep dive to embedded controller and create some bridges to the BIOS guard technology. And of course, it will be a lot of details about the BIOS guard itself. So let's start with the security hardware boundaries. So how many third-party components in your laptops nowadays you have? It's embedded controller, it's keyboard controller, it's fingerprints, it's touchpad even, and all these firmwares have their own boundaries. So it's a lot of limitations actually, because all these firmwares have their own update process, authentication, and sometimes these components can be out of threat model for others, but have a path for attack some other hardware components. So, very interesting part, many of these components which we mentioned on the previous slide connected to the BIOS. And of course, they out of the threat scope of the BIOS itself, which is create some interesting room for us of thinking. And security boundaries, it's not a summary of all the boundaries on your system. Basically, it's separated from each other. And of course, if you can break, as example, TPM, and TPM communicating very closely with the BIOS for a lot of security features, then you can basically break these security features from the TPM. And for the long time, TPM been out of threat modeling for the BIOS itself. And Jeremy Boone actually demonstrated interposer from the last year research, and it was very interesting because he exactly did like that. He tried to attack the BIOS from the TPM itself by interposing the messages from BIOS to the TPM and from TPM to the BIOS and just manipulating with them. Trammell Hudson did very similar work, but just physically soldering to the TPM itself. Very good job. And most recent one, it's race condition on SPI flash read write, which is bypassing bootguard technology. And it's also by Trammell Hudson and Peter Junks, which is this research been presented on Hack in the Box this year in Amsterdam. A lot of information already on public, but main message from this research, authenticated once, it's not means trusted forever. One more good example, Alexandre Gazet and Geoffrey Chorney did a research on embedded controller, on BMC, which is base management controller. It's a different one, but also interesting. So basically, embedded controller responsible for a lot of different flows on servers, and it's also responsible for updating multiple firmwares, include embedded controller, management engine, and BIOS itself. So it's direct path to the write to the SPI flash. So basically, if embedded controller is broken, it's break all authentication for the BIOS, it's break all authentication for the embedded controller update process, and it's break security boundaries. Why we start looking on embedded controller? Our point of research being on the beginning just go deeper on the BIOS guard technology. But we found a lot of interesting relations between embedded controller, BIOS guard, and the BIOS. So, and especially embedded controller involved in authentication process between embedded controller and the BIOS before some flow started. But we will be dig on this a bit later.
Okay, so when we needed to start this study, we needed to discover a bit what was actually running on the embedded controller. We needed to dig into it. So just to give you a quick overview of what is really an embedded controller, it's a very small microcontroller. It will be responsible for many things for you. Silently, we will not see it in action, but it will be responsible for power management, thermal management, also responsible for keyboard press management. In the past, it has also been involved in many security features. For example, it has been used for the implementation of BIOS supervisor password derivation and verification. Some code were hidden inside the embedded controller. Like Alex said, we found that it is also responsible for implementing some specific parts of the BIOS guard implementation, and that's why we wanted to dig into it. And also something that is very important from an attacker point of view is that even if your main processor, your main CPU is not running, the embedded controller is always running. As soon as there's a power on the motherboard, the embedded controller will be running. We have been mostly working on Lenovo Thinkpad laptops. For this laptop, the chip used comes from microchips, the MEC 16-something family. The RAM size is around 280K. It's on some unusual processor, which is compact. Quite often we find it inside the embedded controller. The embedded controller can be seen as a collection of logical devices. That is, you can think about it as services that are exposed by the embedded controller. There is, for example, keyboard controller services, some communication channel with the operating system through a API, a service that exposes the internal flash of the embedded controller. That's very important because that's where its firmware is stored. And that's something that could be very interesting to hide code or hide something, again, if you are an attacker. Okay, now if we place this embedded controller on the system on chip, you can see that it can communicate with the battery through SMBus. Sometimes it will authenticate the battery, things like that, or just get its status, its load status, and this kind of information. On the other side, it is connected to the main processor through an LPC, low pin code bus, with the main processor. And for example, if your main processor wants to know the charge level of your battery, it will go through the EC, get the information, and things like that. So we know there are links and communication between the main processor, mostly the UEFI BIOS and the embedded controller, and we wanted to map all this communication channel, all the endpoints exposed by the embedded controller. From the documentation, we know that the logical devices can be exposed on the LPC bus from the EC. The LPC bus is itself a logical device that you can configure to expose other logical devices. And if you want to do that, you simply write into memory, into special configuration registers, and you say, okay, I want to expose these logical devices at this address on the LPC bus. So from there, the methodology is quite straightforward. On the EC firmware, we have been reversing a lot the embedded controller firmware. You have a small extract on the right. We have been reversing a lot the embedded controller firmware, trying to find all the location in the code where the embedded controller configures this LPC bus to find all the endpoints it was exposing. On the other side, on the UEFI BIOS side, we've been looking for all the communication with the EC, mostly looking for a dedicated protocol from UDK2 SDK and also from specific modules provided by Lenovo. Namely, it was ECIO DXC and ECIO SMM, which are responsible for the communication with the EC. So once you do all that work, you're able to precisely map all the logical devices that are exposed to the host and how you can communicate with them. For example, if you want to communicate with logical device number 2, which is ACPI EC0, communication channel 0 with ACPI, you will simply talk on IO ports 62 and 66, basically. And we will speak more about this because this communication channel can be used to update the embedded controller.
Now let's switch on some attacks on embedded controller, especially on the update process on Lenovo Thinkpad. But before we started digging in our own research, we want to highlight previous research Alexandre did in embedded controller in 2011 from Hitachi and made presentation on Ericon where he exposing some attacks on SMI handlers from the embedded controller and break the keyboard controller too. So, and Matthew Chapman and Hamish Coleman did very interesting functional research on it and provide us a lot of pointers. So, how looks eSIM firmware update process in general? Most of the vendors like Gigabyte, Asus Tech, they don't have any authentication for embedded controller firmware. That means they just basically allow you from the host send a sequence of the commands to the embedded controller to start update process. So it's just like a design issue, but they just don't authenticate the firmware. It was like very, very surprised about that. And they even don't log the host to write to the to initiate communications with EC. And actually, we was thinking, okay, it opens the doors for some interesting malicious activities, and the ways to gain persistence actually huge. First of all, multiple vendors, for the recovery process, they didn't log the GTAG on the board. So basically, of course, it's not soldered, but the pins exist, and easy to discover with JTagulator what kind of pinout it has. And sometimes documentation also on public or leaked many years for similar controllers. And you see update tool from OS usually have everything to communicate with embedded controller and recover all the sequences of the commands if it's not other BIOS components involved in this process. So if the BIOS Dixie driver is involved as on Lenovo ThinkPads, so it's also possible to basically attack Dixie driver or SMM driver and make a second stage which will be attacked directly the embedded controller. And actually, this specific attack, it's out of scope for threat model of embedded controller update process in many vendors. So, and even if we see image have authentication, additional authentication on the BIOS side, it's actually separated by design because you authenticate embedded controller image, then send a sequence of command for the update process. That's raised some questions about possibilities for the race condition, which we'll discuss later. But what kind of impact in update process authentication bypass can be? Actually, embedded controller, it's very interesting place for a persistent storage to store some malicious rootkit. And this rootkit can be signal something to the main firmware known as BIOS and load additional components to there. It's very interesting possibility, and most of the teams who think about firmware security and the BIOS security in the terms of forensics, they look on spy flash, but don't think on embedded controller as a place for the persistence. Our target system for research, it's been mainly Lenovo Thinkpads. We look on the Gigabyte and Asus Tech just briefly, and it was not interesting for embedded controller specifically because they just don't authenticate it. And we think, like, okay, let's take one which is used in enterprise, and P40 and P50 was our main target. So for P50, it's newer chip from Microchip 1653, and update tools basically only initiate update process for EC, but BIOS actually have full responsibility for flashing. So main Dixie driver, it's EC firmware update Dixie with this GUID, which is very interesting place to look. But first of all, we was like, okay, how the update package for EC looks like. We recover the structure, which is have obvious signature EC on the beginning, but after that, version, file size, image size, and which kind of algorithms involved for authentication process. Next slide, actually, we have Lenovo Thinkpad update process, which is starting from operating system with TDK Phoenix framework and continue on SMM driver, which is basically make verification first and then the function responsible for flashing update to the embedded controller itself. And we recover interesting messages on update tool from operating system level, and this tool actually have some comments. This system-wise EC firmware update is unsigned. It's very interesting point, which is take us in the place where we start looking on TP40, and for us was surprised. TP40 doesn't have any authentication. It's used the same, almost the same Dixie driver, but don't authenticate firmware itself. It just basically take embedded controller image from the operating system, mapped on specific address, and then after that Dixie driver read it from this memory and flash it with this sequence of commands. So interesting, right? But what's the impact? So we have many comments. Okay, how you will be reuse this sequence of commands if you have a locked host, or how basically it can be used with active bootguard. And just for reminder, bootguard is a technology which is armoring boot sequence. Basically, it's make additional root of trust and hardware for secure boot on your systems. And if you want more information, here is a link. But main interesting point, the bootguard doesn't cover all the Dixie firmware volume on the P40. And there is a driver which we've been looking for. And this driver, it has actually everything to flash embedded controller firmware. And I was thinking, okay, what if we just reuse this driver from UEFI shell? And this particular part was open additional possibilities for the supply chain attacks. So, but okay, but what if we use this driver and patch just one command in P40 for basically avoid the authentication and take only the flash part for embedded controller? So let's try look deeper a bit how the signature check on P40 looks. It's take update image, mapped OS update tool, basically update image mapped to specific address from OS. Then it's validation for verification the image is correct, and secure flash, its specific public key in the capsule update image with full firmware includes the BIOS, and it's basically mapped by Dixie driver to the hop. Hop is specific runtime structure, which is kind of a list with the structures, objects inside the BIOS runtime. So then the Dixie calculate the RSA verification is correct. They use the signature from embedded controller and use this public key, which is basically secure flash public key. If signature is correct, they enable true to Boolean variable, global Boolean variable. And if signature true, then update process started for flashing the new firmware to the chip. So here is the compiled listing. And I will highlight most interesting part. So basically, we get the EC image hash, verify EC image hash, and it's two separated flows, right? So, and just one Boolean variable. Interesting. So, but what if we separate verify and flash? Looks like it's kind of state machine which is have possible race condition, right? So for me, it looks like obvious place for race condition, but not that fast. let's think about how we can attack P50. And P50 actually have a stronger security boundaries, and especially boot guard working correctly. That means we can't, without disabling the boot guard, attack from the UEFI shell and reuse the Dixie driver. So let's try harder on P50. So host flash access needs to be enabled. First of all, Lenovo make it host write and read from the host locked. And for unlock command, it's used like just simple sequence. So we need send this sequence and with a static password, which is shared between BIOS, Dixie driver, and DC. And after that, we unlock the possibility to write. Easy, right? And what if we just replace the sequence? So, because also we have a static password, you remember maybe one of the first slides where we're talking about the connections between BIOS and embedded controller, ephemeral value. So, in Lenovo it's static. So, basically, this static password is just hard-coded in the Dixie driver and easy to recover, and it's sent just to command to unlock the host, right? So, can we basically just easy do some replay attack? Unfortunately not, because it's some additional bit set to lock embedded controller before update will be started. And basically this lock on early stage BIOS, then BIOS rebooted on reset vector and only start update after that. So authentication no more possible on EC without reset, basically. Lenovo disclosure timeline, so we submit to Lenovo PCert, they assign us CV and make with us additional call where we describe all the issue details, and after that we agreed about what kind of the directions for patch it can be. Thanks for collaboration with us. And we see takeaways. So where we was looking on the BIOS guard, ephemeral value authentication is static. So basically not very hard to reply this stuff. Can be abused in some scenarios when EC rootkit has possibility to be involved. And we think EC BIOS guard ephemeral value support for this laptop lines, it's not fully implemented, or it's just like try to save some time on this update process for performance reasons, we don't know. And boot guard does not fully protect from rush update in runtime, as we've seen on the P40 in some cases. And what the BIOS guard would have a change? So let's make a deep dive to the BIOS guard technology. And BIOS guard technology actually very interesting because this technology been introduced from the Broadwell lines, and especially it was mostly have some marketing information from Intel, but not a lot of details. So rationally, BIOS guard, it's a technology which is armoring SPI flash and try to remove responsibility from SMM for write and read to the SPI flash to something else. And here it appears like multiple components of this technology we'll cover on our talk. And main thing, they remove write and read to the ACM model. So BIOS guard known as a platform flash armoring technology. And yeah, it's basically control access over ECM, and PCH logs the SPI flash access, not rely on the PFAT. So BIOS authentication mostly embedded an ACM model, and actually ACM model for BIOS guard is encrypted by microcode. And it is a game over for malicious updates. It's an interesting question because the technology is super complex, and you can see on our next part of presentation how and where it can be misconfigured. So Also, we have multiple components involved for the security on the Intel platforms. And interesting thing, all these technology and features is disconnected from each other. Think about boot guard. It doesn't communicate with the BIOS guard or verify each other at all. So it's totally separated features. And when the BIOS guard involved in the boot flow protection, it just transfer control to the next stage, to the secure boot. But like it's not really well connected. So that means security boundaries can be very interesting in this place. But let's dig into BIOS guard feature overview. So first of all, remember this link on the bottom, because this slide, it's basically been found there and very moved us forward in our understanding how the BIOS guard works. So first of all, we have a BIOS image where the header and BIOS guard script embedded. And actually after that, sign-in server signs this package and creates the BIOS guard update package, and we recover all the format how the BIOS guard update package looks like. So, and flash update tools communicate with the SMM drivers, and after that, actually, only after that, ACM takes control on it and make active flashing part. So, Lenovo Thinkpad PFAT update process use Lenovo TDK tools, of course, and framework have a pretty similar model. When it's mapped on specific address, the BIOS image, trigger BIOS guard tool over SMI handler, which is work with a CPI. Basically, a CPI have specific region which is trigger SMI handler. It contains specific values. So after that. BIOS guard update package basically was mapped to the memory address with the size and IO trap address. And IO trap address actually a trigger for the PCH. And BIOS guard SMI sets the BIOS guard directory. BIOS guard directory actually huge structure. We will talk on the next slides. And very interesting. So, and this directory contain address of ACM and trigger MSR. And actually all this MSR is undocumented, and we recover over reverse engineering of the Dixie drivers which kind of flows of MSR should be called. So, and ACM triggers microcode flow to verify and apply BIOS guard update to reboot machine. So you can see here is a decompiled flow for initialization stage of BIOS guard update process. Here is resources which we used for the BIOS guard research. It's mostly information which is available from Intel, but not directly described all the features which is basically have implemented on the BIOS guard technology nowadays. Also very good introductory presentation from the Justin Johnson from Dell Firmware Security. And I briefly look on this BIOS guard technology in my offensive con in 2018. So of course we did a lot of cross-analysis between American Megatrends, Phoenix, and it's basically show us some pointers where we should dig in.
Okay, now we'll present to you the recovery we've made on the BIOS guard interface, and we'll start with the interface at hardware level, as exposed by Intel processors. For this, what we're going to tell here, we have mostly work on Lenovo P50 BIOS implementation, which is Phoenix-based BIOS, and also the processor was an Intel Skylake family. So we have the hardware interface exposed by the processor to support this BIOS guard feature. Of course, it is exposed in the form of a set of MSRs that you will manipulate to activate and to trigger the feature. The first MSR you will want to interact with is the MSR OXCE, and in this one you will simply find a flag that tells you if the feature is supported or not by the CPU. Next, the next very important MSR register will be MSR 110. In this one, it's like a status registers for the BIOS guard feature. 2 bits are especially important, the 2 lowest one. One will tell you if the feature is enabled, and one will tell you if the feature is locked or not. This is a read-write register, so you can modify it. Okay, so how does BIOS guard work? It has, of course, hardware support both on PCH and embedded controller part. And when it boots, these controllers are locked. So at the boot time, BIOS guard feature will, in the module SC init, we believe it is for silicon init, will actually generate an ephemeral value using the RD run instruction from the processor itself. And this value will be buried into hardware when you write it into MSR 117. And this ephemeral value will also be sent to the embedded controller. In the code we have been reversing, we didn't find any use of it on the embedded controller. And how it works is that at a later time, at runtime, when you want to trigger the BIOS guard feature, it will, the BIOS guard hardware support will use this ephemeral value to kind of authenticate itself to the PCH controller if it wants to write inside the SPI flash to write the BIOS, for example, or authenticate itself to the EC to prove that the update attempt comes from secure origin. And yes, and once you have written into this MSR 117, the value is totally discarded. That means that even if you have code exploitation code, you are able to run code at the operating system level or even in SMM, you will not be able to access this value anymore. You cannot recover it. Okay, then we have a very important structure that is the BIOS guard platform data table. For now, let's just say that it contains all the platform-dependent static configuration of the feature. It's a very important feature. Also, it is initialized quite early in the boot process of the boot. Sorry, and what happens is that it computes a digest of this table once it is set up, and it is this digest is written into a set of 4 MSR from 111 to 114. That means that we believe this register MSR being write-only, or they are locked once the feature is enabled and locked, and that means that as soon as you have locked the feature, this configuration is immutable. You cannot modify it anymore because hardware support will have the value of the digest. And if you attempt to modify it, then it will be able to detect the modification. So at this point, we are in a PEI phase very early in the boot. That means the BIOS guard feature is entirely set up and locked down. And then we will see how we can use it at runtime. There are 2 other MSRs that we'll use at runtime. The first one is 115. Basically, in that one, you will place a pointer on all the parameters, all the arguments of the call you want to make to the feature. We will detail later what are these arguments. But for now, let's just say that you place a pointer on the parameter of the operation you want to execute in MSR 115. And then you want to trigger the feature, and you simply write into MSR 116. It's like a syscall or trigger for the BIOS guard ICM. Speaking about the BIOS guard ICM, of course, we are quite on the boundaries between software and hardware. You can think of this ICM module as a kind of software plugin for the hardware support. It comes as a file inside the BIOS image. Its format is quite close to the one to the bootguard ICM module. From all the module we've been able to recover, the size is always around 30K of code. It is signed, of course, by Intel, and like Alex said, it is fully encrypted, so for us it's a pure black box. Still, we expect this ICM module to implement the BGPTD hash digest verification, the update package signature check, also verification of the signature on the update package. We expect it to implement the script interpreter. We will tell more about the script later also. And also to implement all the flash SPI access and the communication with the embedded controller if this feature is used by the implementation. And yeah, these ICM modules come as a binary blob provided by Intel to the OEM. So that was for the really hardware support, hardware interface. And now we will look at the software interface of the OEM, and in this case Lenovo, use that feature to implement a secure flash update. We have the BIOS guard directory. That is it's a top-level structure that contains all the parameters that you need to pass to request a BIOS guard operation. It's very simple. It's an array of 6 pointers. The first one is a pointer of the ICM module, the second one a pointer of the BGPTT, and the third one is a pointer on the update package, all the elements you want to write into the SPI flash, to say it simply. The third last is still mostly unknown to us. Yes, they're just a quick bit you set if you want to say that one entry, one pointer is in the structure is present or not. So this is the BIOS guard directory. Then we have the BIOSGuard platform data table that we've been spoke already. So it contains all the configuration, or the static configuration of the protection, of the BIOSGuard feature. It contains, for example, the I/O ports that will be used to communicate with the embedded controller, and the commands that we suppose are used to perform the update with the embedded controller. Some very important things also, it contains a digest of the public keys that are used to sign the chunk of the BIOS update firmware, so that the BIOSGuard ACM can verify that it's signed with the proper key. And the cornerstone in this table are the last fields, which is SFAM array. So this structure describes actually range of protected SPI flash ranges, SPI flash addresses. And yeah, like we saw just before, all this configuration is sealed very early in the boot process. So to describe more SFAM ranges, it's just a very simple structure with start address, end address, and you will describe a set of ranges that you want to protect with the BIOSGuard feature. And as soon as you describe a protected range like this, it means that you will request, you can only write inside these ranges with signed operations. And it's also interesting to make a cross-analysis of these ranges with information we can get from the flash map structure to analyze what kind of, what parts of the BIOS image are really protected by these ranges. For example, main firmware, recovery firmware, etc. Okay, so now we have the configuration of the protection, static configuration of the protection, and we will want to perform some kind of operation. For example, to write some parts of the flash with a new firmware. We will build a BIOSGuard update package, which mostly contains 4 elements. First is a header, then a script, then the buffer, that is the data that you want to write into the flash, and then at the end, the cryptographic material. Basically the signature, of course, of the buffer that is come just before. Like Alex said, the feature, you invoke the feature with some scripts. Scripts can be templated for signed or protected operation or dynamically generated at runtime by a dedicated module. We can find all the templates that are used by the BIOSGuard implementation from Lenovo in a dedicated structure that is appended at the end of the UEFI image. So we have this IPAC directory. It comes simply from the magic of the structure. So we have this directory that allows you to find all the files that are used as a template. The file that's in the green part and the directory is at the very end in purple. So we have been reversing this structure and we are able to dump all the files that are described inside this. The first one is emg.org, basically just the main UEFI image, the main update that we want to write. Then we will have pub head, basically a template for the header, pub scrp, which is a template for the script, pubcert, which is a certificate. It's a template embedding the public keys and the signature of the chunk we want to write. And pubsign is a big file. It's just a collection of all the signature for all the chunks of the main images. And all the dummy files, a file with a dummy in the name, seems to come from an artifact from the SDK, and there are specific checks into the code that verify that these files are not used in production. No, okay, we found lots of templates into this IPAC structure. We will detail them a little. First, we have pubcert.bin. So, like we said, it contains all the cryptographic material, mostly the public key that has been used for the signature. It's RSA signature and SHA-2 digest. And we have a big placeholder for the signature. You have the public keys and then the signature of the placeholder. It is overwritten at runtime with the signature that is for the chunk you want to write into the flash. Then you have the template for the header. So few informations. The most critical one is the flags field. Inside that one, you have a specific bit that you have to set to indicate to the BIOSGuard ACM that the operation you are going to perform, either write or erase, is actually a signed operation. So it needs to check all the stuff, check the signature of the buffer you want to write, etc. The other field is a platform. For us, it will be Skylake in this for this laptop, P50 Skylake processor. But this platform have to be coherent between the various fields we can find. So we have almost all the elements we need to build a BIOSGuard update package. So we will have our header. the script that will be modified a little, we'll see how. Then our update buffer. The main image is split into chunks of 1000 bytes. And then at the end, we have the signature of these chunks if you request a sign operation. And like we said, we are able to build then the BIOSGuard directory with a pointer at the SCM, pointer on the BGPTD, pointer on BIOSGuard update package. We take a pointer on this directory, replace it into MSR 115, and we trigger the execution with write inside MSR 116. So we trigger the execution of the BIOSGuard SCM. What it will do is that BIOSGuard SCM will check some stuff, like for example, that the BGPTD has not been tampered with, check the signature of some parts, and it will start the execution of the script we pass to it. As the ACM is fully encrypted, it's purely black box, so we have only been able to recover some very partial information on about these script languages. From what we've been able to recover, it seems to be a fixed size instruction set, 8-byte instructions. It always starts with 0, 1, and always end with FF. And we have a few instructions that we've been able to understand, or at least guess. There is one to set the flash address where you want to write, and there are instructions to say, okay, I want to erase some chunks, or instructions that say, okay, I want to write that chunk. And yeah, like this, like the interpreter is in ASM, fully encrypted, we have no access to it. So it's difficult to say more. Like we said before, there are two kinds of scripts. You can have dynamically generated scripts for unsigned operation. In this case, scripts are really basic, only 4 instructions. It's only a start, set address, write, and end. So very, very basic. In case you use templated scripts for signed operation, then we have a larger program, which is 26 instructions. We said that this script is a template because the second and third instruction will be modified on the fly with the correct flash address that you want to write into, and the third one you will patch the chunk size, the size of the buffer that you want to write. And of course, like we said, really the cornerstone of the protection is that if you want to write inside SFAM described region, you need to have a sign operation, otherwise it will raise an error.
Yeah, we have open questions in this research because we really not understand, as example, why BIOS script it can be modified in runtime. And from the previous slides, you can understand how much possibility for the attacker this BIOS script has. So it creates really large attack surface in our understanding, and also like complexity of technology itself, it's kind of impressive. Also, we was thinking, okay, ACM is encrypted, and basically, we can control when we load the ACM, and also we control the BIOS script on our side. So it's actually open a lot of possibilities for the black box fuzzing for ACM itself. Even it's encrypted, we can dump it because it's actually executes on the locked hash. But we tried our best. Actually, will be described a bit later on experiment slide. And so, not for this research, we also found a lot of interesting codes. As you can see, like bad BPDT and script syntax, unexpected opcode, all of these error codes actually can be additional pointers for black box fuzzing. And you can basically reduce the scope by understanding what you exactly fuzz and where you failed. So what kind of experiments we did? So actually, we did a lot of ACM fun, honestly. So we tried with Intel hardware debugger DCI access to ACM memory. Unfortunately, you need additional unlocks to debug ACMs on the Intel platform, and just normal ACM DCI doesn't work properly. So we can't dump decrypted ACM from the memory, but it was a good try. So we tried to replace BIOSGuard ACM on different versions of this ACM on specific platform, and it's with older versions it's temporarily breaks the laptop, but thanks God it can be refreshed and recovered, and because we just have one target platform in our research. And remove ACM from the update image itself, it's basically create interesting flow because it starts loop of weird reboots on S3, which is sleep state, and after few tries it recovers the previous state of firmware. So, and as a conclusion, we basically want to make a note. So BIOSGuard feature, it's very complex. It's a lot of different parts which can be something go wrong. And strong dependency OEM vendors to Intel, because OEMs doesn't control ACM, and ACM version not very recently get updated. So it's actually, we notice many platforms just use the same ACM, and even sometimes newer generation use older ACM version. It's maybe not older, just not BIOS guard script evolved. So Lenovo AC support, embedded controller support for ephemeral value generation, and also for the BIOS guard scheme. It's not very it's not implement all the features which is Intel actually proposed on the public, and also it's probably just not follow the reference code or whatever, so it's still limited. Its possibility for other firmwares also can be updated more securely with the BIOS guard, but we don't see yet this. And many implementation details in hands of IM, which is like room of misconfiguration or supply chain attacks. So yeah, where implementation can be failed. Secure flash access regions is FAM, which we show to you how it can be mapped to the flash map. It can be misconfigured. If you miss something, so then it can create a room for the attacker to basically use this possibility to basically modify some Dixie models or even SMM if OEM can be failed. And also signed versus unsigned operation with BIOS guard script create a lot of concerns on our side. Communication between BIOS and EC implemented correctly, but not static session password, right? So, and recovery process, of course, involved for the BIOS guard flows too. And recovery, it's very, very difficult to be make it secure. So it's also kind of interesting place to look for the future research. Thanks a lot for everybody who support us in this research, and especially we want to thank Igor and Ilfak for great support of IDA Pro, especially on the ARC disassembly part, because it's just great. Thank you, everybody. We have some room for questions.
Hi, I'm just curious on how you arrived at Lenovo and if you did do any preliminary tests.
Excuse me, can you speak a bit more louder because we can't hear you?
Hello.
Yeah, good.
I was wondering at how you arrived at Lenovo and if you did any other preliminary tests with, say, Dell and HP, and if you suspect that they have similar vulnerabilities.
So, probably, but we don't look on HP or Dell just because we have on our, so we just use the laptops which we have on our table for as a target platforms. That's it. So it was main purpose. But answering on your question, because most of the vendors use the same practices, probably it can be same problems on the other vendors, but we don't know.
You mentioned that T540 doesn't have EC authentication.
No, it has.
Sorry?
It has EC authentication.
Okay, for in the boot process or
P40 doesn't have, and P50 has.
Okay, but I mean in the boot process or when updating the EC? Is it which kind of authentication? Both or?
Excuse me?
Like for the boot chain, does it verify the EC image also, or this authentication is for when updating the EC, the firmware?
Are you from Lenovo? You try very detailed asking the questions.
Where is this authentication? Sorry, you mentioned that.
Let's maybe discuss this later in the room with the questions, because I think it needs very detailed explanation. We will take like 5 minutes for explaining.